Hello, everybody. Welcome to the next Euroviz 2020 session. This is a state-of-the-art report session. It's a session about flow visualization. My name is Holger Theisel, University of Magdeburg. I am the session chair, so I guide you through the sessions, and I'm collecting all the questions you guys hopefully are posting on YouTube and Discord. We have two very interesting, and I can say this because I read and saw these movies already, two interesting presentations. The first one is a survey of seed placement and streamline selection techniques, and the authors are Sudhanshu Sain, Roxana Bujak, Christoph Gard, and Hank Childs, and Sudhanshu is going to presentation. Have fun.
Hello everyone. This talk will be presenting a survey of seed placement and streamline selection techniques. I hope you enjoy the presentation. Here is an outline for the talk, and we'll set the context by discussing what flow visualization is, what streamlines are, and why seed placement and streamline selection techniques are important. We'll then look at how our survey classified the large number of works in this space into several categories that adopt different strategies. And we'll end with a look at future work. So let's begin by looking at what flow visualization is and why it's important. Scientists use scientific simulations to model the behavior of phenomena of interest. For many of these simulations, and in particular computational fluid dynamics simulations, flow visualization plays a key role. Flow visualization is a prominent branch of scientific visualization, and it is used to verify that the model being simulated is working correctly or as expected, and it's also used for exploring and understanding the simulation data. Further, its applications range from weather and climate models to medical imaging. Now, flow visualization and analysis can be performed in multiple ways. There are direct, geometric, and texture-based methods. Direct methods use things like arrows and color maps. So an example of that would be the image on the left. Geometric methods use distinct objects to convey information about the flow. For example, consider a curve being used to represent the trajectory of a particle moving with the flow. Typically, a sparse number of these distinct objects suffice, but identifying where these objects should be placed is hard. Texture methods are an integration-based approach which use textures to provide dense, detailed flow visualizations. During this talk, we'll be focusing on geometric methods, and in particular, the problem of selecting the optimal set of objects. The geometric object we focus on in this talk is called a streamline. Streamlines are one of the most commonly used techniques to visualize flow. A streamline is defined as the path traced by a massless particle as it moves with the flow. The path is an integral curve that is the solution of an ordinary differential equation, and the curve is tangential to the vector field at every point. When a steady-state vector field is considered, the integral curves are called streamlines. When an unsteady or time-varying vector field is considered, the integral curves are called pathlines. Now it's worth mentioning that the majority of work that has been done is for streamlines, since a steady-state vector field is typically more practical to study than an unsteady-state vector field, while also still providing valuable insight. So how is a streamline calculated? You use a process called particle advection. You place a particle at a seed location and then displace the particle according to the underlying field, and this will require interpolating the velocity at arbitrary locations. This results in an integral curve which corresponds to the trajectory the particle travels along. There are different numerical methods that can be used. The easiest is an Euler step. RK4, which is Runge-Kutta 4, is a higher order advection scheme, which is typically used in research work because it is more accurate. So now a challenge in flow visualization is determining which streamlines to generate or select in order to represent the flow field. Algorithms have strategically placed seeds or made an informed selection of streamlines, or some hybrid method which uses both to generate a representative set of streamlines. Although there are many integration-based techniques, we focus only on integral curves and particle-based systems in this report. The rest of this talk focuses on topics pertaining to seed placement and streamline selection techniques. So why are there so many different techniques for seed placement and streamline selection? That is what motivates this research. The first reason is that streamlines, although very useful to understand a flow field, must be used carefully since they are not easy to select. If too many streamlines are calculated and displayed, this would result in a dense and cluttered visualization. On the other hand, if too few streamlines are used to represent the flow field, then there is a high likelihood that important features will be missed. This research has proposed strategies that provide a clear and insightful view of the domain flow behavior. These techniques are also researched for other flow visualization tasks, such as selecting streamlines that are similar to a query streamline or in particle-based flow visualization systems. So with the seed placement and streamline selection task, what we have is a non-trivial problem with no formal definition. So algorithms typically state some set of desired characteristics they want to achieve. These include things like having a uniform distribution of streamlines, capturing interesting features, aesthetics, like longer streamlines look better. You would typically want minimal occlusion in a 3D setting, good spatial perception cues, frame coherence, maximum information content being encoded in the extracted streamlines, and of course you want a fast algorithm. So these characteristics can be split into qualitative and quantitative, and most research has focused on improving or supporting additional qualitative capabilities of algorithms to improve how information is conveyed through visualizations. So what is a good or better algorithm? From the perspective of how research is proposed, this is very use case dependent. For example, you can compare how well two algorithms capture features, or if one algorithm is quantitatively faster or better for the same use case. What do we consider when comparing various techniques that might seek to address different objectives and achieve different characteristics? Essentially, what characteristics of these algorithms are we interested in? We identified three evaluation criteria: computation, regions of interest, and redundancy. Now, there is a trade-off involved when considering maximum information content given a fixed budget or a fixed number of streamlines that can be used. Here is an example to give you an idea of how a set of streamlines might be evaluated, particularly with respect to regions of interest and redundancy. Each image has 50 streamlines. Image B captures features better. We can see that several critical points are clearly visible. Now, for those that are unfamiliar with this space, areas near critical points are considered regions of interest in a flow field. A critical point is where the velocity is zero, and there are different kinds of critical points that are identified depending on the behavior of the flow surrounding the critical point. Image A, however, doesn't highlight any of these features well, and in fact, there are several redundant streamlines which show nearly parallel flow. Overall, these algorithms can be split into automatic and manual techniques. Automatic techniques are then subdivided into 3 categories after 1 level, 8 categories after 2 levels, and 16 categories after 3 levels. Manual techniques are subdivided into 2 categories: techniques using interactive tools and techniques using domain information. In this presentation, we'll focus on the automatic techniques. Here is the complete classification of the automatic techniques. At the highest level, these are classified into density-based, feature-based, and similarity-based techniques. These classes of techniques have generally been accepted in the literature. Our survey further classified density-based techniques into view-independent and view-dependent techniques, which have 2 and 3 subclasses respectively. Density-based approaches typically attempt to generate a uniform distribution of streamlines either in object space or image space. If it's an object space, it's a view-independent approach. If the uniform distribution of streamlines is desired in image space, it is a view-dependent approach. We further classified feature-based techniques into flow topology, derived field, and user-defined scalar field guided techniques. Of these, flow topology and derived field have 2 subclasses each. Feature-based methods try to highlight and capture regions of interest in the domain. They do this by explicitly extracting the flow field topology, that is calculating the locations of the critical points, or deriving useful scalar fields to guide the algorithms. Within similarity-based techniques, we identified spatial distance, shape, and machine learning guided techniques, each of which had 2 subclasses. Similarity-based approaches cluster similar streamlines together with the goal of reducing redundancy. We'll start by looking at the subclasses of density-based techniques. The first subclass is view-independent techniques. The objective of these techniques is to generate a uniform distribution of streamlines in object space. To achieve this, there are two classes of strategies, local seeding and global seeding. We'll start with local seeding. These algorithms iteratively select a seed that is a minimum separating distance away from existing streamlines, and all candidate seeds are stored in a queue. These algorithms produce evenly spaced, uniform distributions of streamlines and support simple optimizations. However, a large number of distance checks are required. Important features can be missed if the representation is too sparse, and these techniques often produce redundant streamlines if the minimum separating distance is too small. Algorithms using a global seeding strategy iteratively placed a seed to fill the largest void in the domain. A threshold determining the stopping criteria enables density control for these techniques. To identify large voids, these works have calculated the Delaunay triangulation over points, identified the largest segment in orthogonal flow, and tracked empty connected cells to determine where the next seed point should be placed. These approaches provide a uniform distribution of streamlines and often better aesthetics than a local seeding strategy. However, they also produce redundant streamlines as the number of streamlines increases. They can also miss important features, and in most cases, they are not suitable for 3D. The next subclass is view-dependent techniques. The objective of these techniques is to generate a uniform distribution of streamlines in image space, and there are three subclasses of strategies: use of filters, image space seeding, and the use of occlusion and projection. The use of filters were among the first efforts at generating aesthetically pleasing sets of streamlines. These techniques modified an existing set of streamlines until a filtered version of the streamline image reaches a desired visual density. These techniques would make changes suggested by an oracle or at random until a desired distribution of streamlines was attained. Although these techniques produce a uniform distribution of streamlines, the convergence time was high for a large number of streamlines. The next class of techniques used depth maps and placed seeds in image space while advecting the seeds in object space. These techniques reduce cluttering and unnecessary computation while producing evenly spaced streamlines in image space. They can, however, miss important features if too sparse or contain redundancy if too dense. The last class of techniques evaluate 3D streamlines by considering the image space projection of the streamlines and the occlusion caused by it. These techniques use occupancy buffers and measure streamline importance. Here is an example using opacity optimization to address occlusion of interesting regions of the flow field. These techniques are good at highlighting regions of interest and capable of being interactive and frame coherent when using hardware accelerators. Feature-based techniques try to highlight and capture regions of interest in the domain. The first subclass is flow topology techniques. The objective of these techniques is to guide seed placement and streamline selection using critical point locations and separatrix as the initial set of streamlines. When using critical points, the strategy is typically to use a critical point specific template to accurately capture behavior in the neighboring spatial regions, and then the remaining domain is filled using something like a local seeding strategy for coverage. These techniques highlight flow features, but could introduce redundancy with respect to how coverage is attained. When using the separatrix as an initial set of streamlines, these techniques then operate on subregions within the flow to place additional streamlines. For example, this could be done by uniformly placing a seed along the longest orthogonal path in each subregion of the flow. These techniques work well and produce sets of streamlines that accurately capture the vector field information. However, they are currently limited to 2D. The second subclass of feature-based techniques is using derived field information to guide seed placement. Entropy is derived from the vector field and enables the use of vector field information content to guide seed placement. These works have considered the use of entropy in both object space and image space. These techniques highlight flow features, and entropy can be computed fast in parallel. Several other derived field characteristics such as curvature, torsion, helicity, gradient, and curl have been used to generate streamlines that highlight desired and, in some cases, specific flow features. Similar to entropy, these features can be derived fast using GPUs. Using these derived features by itself, however, does not guarantee a good visualization, particularly when considering occlusion and clutter in 3D. However, these techniques are good for quantitatively measured vector field reconstruction. The third class of feature-based techniques covers multiple works that use user-defined scalar fields to select streamlines. In the example here, a scalar field called the box counting ratio is used. This scalar field provides a measure of the space-filling properties of a streamline. Using different thresholds for this user-defined scalar field, we can see how the domain can be visualized using 5000, 110, or 8 streamlines. A problem with density and feature-based techniques is that they fail to provide coverage without introducing redundancy. Similarity-based approaches address this by clustering similar streamlines together and identifying representatives. The first class of similarity-based techniques use spatial distance to measure similarity or dissimilarity between streamlines. The first subclass uses distance measures to select a set of streamlines that are dissimilar from each other. This involves performing Euclidean distance tests and computing distance fields with an iterative seed placement process. These techniques provide control of how much information content can be encoded using the streamline selected. However, these techniques were also slow given the large number of distance checks that were required. The mean of closest point distances is the mean of Euclidean distances between pairs of points formed by mapping each point of one streamline to the closest point of the other. Clusters are merged when the distance between two clusters is the minimum of the distance between all pairs of member streamlines. These techniques are good at highlighting flow features and they minimize redundancy. However, they do require large preprocessing times and are limited to similarity in proximity. The next class of similarity-based techniques consider shape. Shape techniques are further classified into point-sampled features and segmentation techniques. Point-sampled feature techniques essentially determine what feature a streamline represents by measuring attributes along the streamline. The streamlines are then clustered based on the identified attribute and the approximated location of the feature. Although faster than spatial distance techniques, these techniques also require large preprocessing times. While highlighting features of a flow using cluster representatives, the current work under this class is also limited to similarity in proximity. To consider similarity between streamlines in a scale, proximity, orientation, rotation invariant manner, segmentation techniques have been proposed. Here, feature vectors are calculated for streamline segments, and then a combination of a similarity metric and a clustering technique is used. These techniques are an order of magnitude faster than spatial distance techniques, but still involve a large number of similarity evaluations. The final and newest subclass of techniques is similarity-based machine learning techniques. There are currently only 2 works in this subclass. When using an SVM for segmentation, the study aimed to use user-identified points to guide the segmentation process in order to account for what a human views as an important feature. The second and more recent study used a deep neural network to generate a representative set of streamlines given a vector field. They first subsample a random set of streamlines, followed by using a deep neural network to produce a 1024-dimension feature descriptor for each streamline. This is followed by a dimensionality reduction and clustering process. The final set of streamlines consists of representatives of each cluster. This technique produced the lowest vector field reconstruction error, but was far slower than comparable methods. Our survey resulted in an ordering of subclasses based on the evaluation criteria we determined: regions of interest, redundancy, and computation. This ordering was determined by considering several qualitative and quantitative comparisons made in the literature. This ordering also serves as a guide for interested readers to find specific sections depending on criteria that are important to them. although there has been over 2 decades of work in this research area, there remain several open problems. The study of unsteady state or time-varying flow fields presents several challenges with respect to interactive exploration techniques. There is also future research required to adapt these techniques to operate within in situ distributed memory settings. An already active area of research, the automatic generation of stream surfaces, is seeing several seed curve placement techniques being proposed. I note that the machine learning technique that uses a deep neural network works for stream surfaces as well. Lastly, a developing and relatively newer area of research is the use of seed placement and streamline selection techniques for uncertainty flow visualization. Alright, that concludes this talk. I would like to thank my collaborators and also all the authors we reached out to for permission to reuse their images. Thank you.
Okay, again, thanks again for the presentation. Now Sudhanshu is live with us and he is ready to take your and my questions. I didn't see any questions coming up in the channel, so I start asking myself a question. The first is about the classification you came up with. One of your classes was the view-dependent techniques, and I wonder why this classical technique of Turks and Banks of this image-guided algorithm, why did you classify this under view dependent?
So I grouped any technique which depended on the image itself, like the angle that you view the image. So for example, those all went into view-dependent technique. Mm-hmm. They used like filters on the final image which would be produced, or considered the final image-based representation of the streamlines and then modified that. For example, if there was another work like the Turks and Banks which applied it to curved surfaces, and so it actually made an impact over there what the final angle that you're viewing the image was from, and then accordingly it would. So those techniques fell into that category in my classification.
Okay, then it makes sense to me. Okay, that clarifies it. Any other questions showing up? Not yet. So I have another one. On slide 10, you had these two examples. This was with the 50 streamlines. One was equally distributed, and one was emphasizing the features. And you mentioned that the feature emphasizing is the better one. I'm not really sure if you can say this, because I think all these guys who just came up with these equal distribution approaches, probably they would disagree, because if they take the measure of being as equally distributed as possible, so how safe it to say this is the worst technique? And giving up this equal distribution pays off in terms of highlighting the features.
So that's a very good question. So one of the big challenges with identifying, what all these works contribute to, one of the main things is the use case. Each one has a different use case and specifies a different set of characteristics that are important to them. And if you look at how the space has evolved over the last 20 years, you can see that initially having a uniform distribution was of most importance rather than anything else, because the initial, especially in 2D, the challenge that they were tackling was if you placed everything uniformly, you get these visual artifacts if you draw very short streamlines, and if you draw long streamlines, they're cluttering in spaces. So the first objective was like, can we use fewer streamlines and still have them uniformly distributed in the field such that they're not missing any features, you're getting total coverage. So that was the initial objective. Certainly if you ask someone what you're more interested in, they might say, hey, I want to have full domain coverage, and capturing any specific feature is not as important to me, or I don't want to have any additional computation to capture any additional feature. Then in that case, they'd probably be more inclined to look at some density-based techniques, which don't necessarily focus on those features. So there is a wide array. My judgment of one being better than the other is likely based on how literature has evolved over time, and the shift from density-based to feature-based, and then saying, what is the shortcoming with the density-based and feature-based? They both have a lot of redundancy to attain that coverage, and that's where the similarity-based techniques come in, where they specifically tackle that problem of redundancy. So over time, characteristics that have been desired have evolved, and as have the algorithms with those characteristics. That's my take on that point.
Yeah, fair enough, makes sense. Other questions? I don't see any questions in the. Oh yes, there's a question in the chat by Wang. Would you please say something more using deep learning for seed placement? What are the challenges and opportunities?
So this is probably not, deep learning is not my area of expertise, but when I think about what the one work that has been done for deep learning for seed placement, and this is something we've discussed in terms of how we can use machine learning in a in situ context, which is basically at runtime, can I decide where I want to be placing seeds based on how this vector field is developing? We've thought about this. I don't think we have a solution for it yet, so I wouldn't be able to give you like you would have to do this, and you would have your answer to it. The one way that we can think of it is that the technique that was used is they don't. So with machine learning, it's really hard to evaluate your vector field, any scientific data set. So firstly, processing that, the size of the data set, all these challenges are probably what you need to overcome first before you start looking at exactly where I should be placing my seed using a deep neural network. I don't know, Roxana, do you have a better answer for how you could use deep learning for seed placement?
Can you hear me? Mm-hmm. Oh, all right. No.
That was the answer. So, thank you.
Yeah, I haven't got to that answer yet, how you would use deep learning for seed placement, though. But the work that was done using the deep neural network was interesting because they used the clustering approach. They used the things that are available in machine learning that it can do well. They had a lot of streamlines. They gave it feature vectors, clustered those streamlines based on those feature vectors, and then were able to identify ones that were distinct from each other by looking at representatives of the clusters. But for seed placement directly, I currently don't have an answer of how that could be done.
Just to explain you guys this unexpected female voice from the background, that was Roxana Bujak. She also is the author of this paper, one of the co-authors of this paper, and she's also the first author and presenter of the next presentation. And because of this, by chance, she was also in this meeting and was answered to give this very short and clear answer. I have another question concerning. I want to talk about the future research. You have mentioned a few points there. What are the low-hanging fruits in this future research, and what are the points where you would say, yeah, okay, I can mention it, but there's not really a decent chance that we solve them in the next few years?
So low-hanging fruit, I would definitely say, is application of seed placement techniques and this is especially my area of work, what I've focused on more in an in situ context. So can you place seeds and generate flow visualizations as the simulation is running? What's the best way to do that? Can you avoid having to save a vector field at all and just generate the streamlines that you want beforehand? So that is, I would think, the lowest hanging fruit that you could do that, and that seems pretty easy. There are already probably people that are working on this. The bigger challenges would be actually applying machine learning techniques in computationally constrained settings where it's expensive to do. You want to do it because it's giving you the results you want, but it's hard to make it fit in the setting that you want. So if you're trying to think of, again, an in situ setting where you're running along a simulation, you probably don't have the computational resources allocated to you to do some machine learning technique. Not yet, at least. And maybe that would be something I could see happening 4 or 5 years down the line, maybe sooner. But low-hanging fruit next few years, I would say, are just application of, given a vector field during a simulation, can you generate your flow visualization right away that you would be valuable to you? And I think that's doable. It's very much within our reach, and I'm sure people are working on it.
All right. Yep. Sounds good. Thanks a lot, Sudhanshu. Are there any further questions? I don't see any in the chat. So thanks again to you, and let's switch to the second presentation. And the title of the second paper is State of the Art in Time-Dependent Flow Topology, Interpreting Physical Meaningfulness through Mathematical Properties. And the authors are, you already know this, Roxana Bujak, Lin Yan, Ingrid Hotz, Christoph Gard, and by Wang, and Roxana is going to give the presentation. Enjoy.
Rule number 1 of making a good presentation: know your audience. So this is kind of weird that I cannot even see my audience. Like, there's no feedback, no nothing. I'm just talking to myself here right now, so this is a bit odd, but well, here we go. My name is Roxana Bujak, and I am going to talk to you today about the state of the art in time-dependent flow topology, interpreting physical meaningfulness through mathematical properties, which is joint work with Lin Yan, Ingrid Hotz, Christoph Gard, and Bei Wan. Okay, why do we care about flow fields? It's because they are actually everywhere around us. Whenever water or air moves, this is a flow field that scientists and engineers are trying to understand in order to be able to do their work. And understanding flow fields is not trivial because the way that they usually occur in nature, they are invisible. And that is where flow visualization comes in, the science of how to make flow fields visible. And the challenges in flow visualization are especially in three-dimensional flow visualization, because for every visualization element that you draw, streamlines, pathlines, arrowglyphs, you have to deal with occlusion. Like, every single thing you draw makes everything that is behind it pretty much invisible. So it is great for a visualization technique if it is able to really focus on the areas of importance, if it's able to capture the underlying structure of the data that we're actually looking at. And one of the most promising techniques in the classical steady case is vector field topology. Vector field topology is able to segment the domain into areas of coherent behavior. The so-called topological skeleton consists of critical points and separatrices, where the critical points are the locations that have vanishing velocities. And the separatrices are the codimension 1 invariant manifolds. Let me explain this in a little bit more detail in a second. So, first of all, the critical points can be classified into sources, sinks, saddles, and centers, pretty much based on the eigenvalues of the Jacobian matrix, which is the flow gradient around the critical point. And around the saddle type critical points, which are the ones that have inflow as well as outflow, the separatrices can be computed, at least in the two-dimensional case, by seeding streamlines in a small offset in the direction of the strongest attracting and repelling directions, which is given by the eigenvectors, and integrating them. And those separatrices pretty much form the segmentation, because in every segment that they produce on the data set, all the streamlines inside pretty much behave the same. Like, they come from the same place and they go to the same place. And there's like no way for them to escape this segment. And so the topological skeleton really gives an excellent representation that is sparse and does not really lose much of the information of the original data, but is like much, much smaller. So that helps not only for visualization to reduce the occlusion, but it also helps for computational purposes. For example, if you would want to just reduce your data before storing it out of a supercomputer. Sadly, flow topology comes with one big problem, and that is it does not easily translate to a time-dependent setting. This has long been known, and I just want to cite Perry and Chong, which pointed out that instantaneous streamlines, which is what the classical vector field topology is based on, have found considerable use even though they are not Galilean invariant and appear to lose physical meaning if the flow is unsteady. And in order to prepare for this work, I went to a colleague of mine who is a fluid dynamics person and asked him, what does physically meaningful mean? Like, what makes a method physically meaningful? And he just pretty much laughed in my face and said, well, I mean, a method is physically meaningful if it gives me the answer that I'm looking for. And so he did not really rule out the classical topology to also yield meaningful answers in certain cases, but not in all. And he just said there's no clear definition of what physically meaningful means. Well, apparently here, Perry and Chang mean that Galilean invariance is a necessary condition for a method to be physically meaningful. And what we did in our survey is to go through all different kinds of papers and try to find out what other concepts that can be defined in a mathematically rigorous way are considered necessary for a method to be called physically meaningful. And we were able to collect pretty much 5 very popular concepts that have a clear mathematical definition, so we can actually analyze if methods suffice them or not, that are very popular and considered necessary for a generalization of the classical vector field topology to be considered physically meaningful. And those are the 5. The first one, we want to have a coincidence with the steady flow topology. So that means if I have a method that is designed to work on fields that change over time, but I feed them a field that actually does not change over time, then I want the output of my method to actually be the classical steady vector field topology. That means the critical points and the separatrices. Well, this is clearly, if we want to talk about a real generalization, right? This is what we want to have. The next thing is we want to have our method to actually produce a partition of the domain. So this nice property that I have those segments in which all the flow behaves coherently, we also want to have this for our generalized method that works on time-dependent data. And the picture here on the right points out pretty nicely what that refers to. The method on the right picture, on the right, would come up with a real segmentation that is not trivial of the domain, while the picture on the left, it locally segments the domain, but not globally. So we want to distinguish between those two cases. The next thing is Lagrangian invariance. So a method is considered Lagrangian or Lagrangian invariant if the features that it extracts behave like they are advected by the flow. So for critical points, those should generalize to pathlines pretty much. And the separatrices, they should generalize to material surfaces, to path surfaces. So this property ensures that no particles cross these boundaries that are produced by the new generalized separatrices. And this can also be found illustrated on the picture on the right, where there are certain path lines seeded that are shown not to cross the boundaries extracted by this method. The next popular method that we came across that is considered necessary to imply physical meaningfulness is objectivity. A method is objective if it pretty much gives the same result, even if we change the observer that looks at a physical phenomenon. So this concept is illustrated on the picture on the left, which shows the von Karman vortex street flow perceived by 2 different observers. So the bottom picture has the observer in the lab frame. So it's pretty much an observer that sits on the obstacle. And the top picture has the exact same physical phenomenon, but perceived by an observer who is kind of moving with the flow. Like he sits in a boat and goes down with the average velocity of that flow, and he perceives a very different picture if we look at the streamlines and if we look at the topology. And so a method is considered objective if they give the same results. And Galilean invariance is a special case of objectivity, which treats Galilean transformations of the reference frame, which is only linear translations and constant rotations, while objectivity refers to complete Euclidean transformations. So there is no restriction on the time dependence of the rotation or the translation involved. And then we went through the whole corpus of literature from the flow visualization side to look at the methods that they came up to generalize classical steady vector field topology to the time-dependent case, and tried to figure out if they suffice these properties or if they don't. We also classified the method based on the approach that the method is working off, and we came up with 4 different classes of approach. And the first one is the tracking of the steady topology. Then we have methods that use reference frame adaptation. We have a big group of pathline classification or clustering techniques, and a group that generalizes the definition of critical points based on scalar fields. And now the end product of our work are those 4 tables, one for each of the different approaches, that collects downward the different methods that belong to the approach, and to the side we have those 5 desirable mathematical properties. And the color coding shows us if a method does suffice this property or does not. And in certain cases there is a mostly it does or mostly it does not, where we have those in-between cases color-coded in teal and in purple. And those 4 tables in the paper, please go there for a detailed look, also have a reference that goes to either the theorem and the proof that this method actually has this property, or to a little counterexample that shows that it does not. I will showcase this principle using one example that does mostly not satisfy those properties, but we chose this as the example anyway because Theisel et al. Thought about this problem like a long time before many of the other methods came along. So we think it's one of the really important works. In their paper, Streamline and Pathline Oriented Topology for 2D Time-Dependent Vector Fields, they actually follow 2 approaches. One is a tracking approach, which we will not look at into now, but one is based on pathlines. And what they do here is that pretty much for each location, they look at the field after projecting it from space-time to the plane orthogonal to the pathline, pretty much. And then classify if this location belongs to a source type, generalized critical points, if the surrounding pathlines diverge away from it, or a sink-like if they diverge toward it, or in either case if they have both kinds of behavior. And you can see a picture of the result of this outcome where those planes pretty much show the boundaries between regions where this behavior changes. So we can clearly see from this picture that for our first column coincide with the steady case. This is not the case because this method actually does not return isolated points, but only regions. Then the next question was, does it segment the area, the domain into areas of coherent behavior? And yes, we have a segmentation here, which can be clearly seen from the picture. Every point belongs to exactly one category, source-like, sink-like, or neither. Then the question, is it Lagrangian? We can also answer this with a no, just from looking at the picture that comes from the paper, because we can see there are pathlines rendered and they clearly intersect those boundaries. So the boundaries are not material surfaces. And to answer the question of Galilean invariance or objectivity, we produced the little counter example that you can see in the schematic pictures on the right. So in the middle picture, you can see a time-dependent vector field where time changes in the upward direction, and it's a one-dimensional field. So space just goes into the sideways horizontal direction. And the grid pretty much has arrows associated everywhere that shows where the vector field goes. And we're looking at the location right in the center of the grid. The red line is indicating the plane that is orthogonal to the path line. So the path line just goes completely in time direction in that picture, and projecting it down to that plane produces the red arrows. So the middle part actually is not going anywhere. On the right it goes to the right, on the left it goes to the left. So this would be classified as a source type generalized critical point by the method by Theisel et al. Now we go to the picture on the right. This is the same vector field after a Galilean transformation of the reference frame. And now we can see that the arrow in the middle points slightly diagonally. So the plane that we look at that is orthogonal to it, again indicated in red, now it goes over across diagonally. And if we look at the vectors at those neighboring points and project them down to this plane, then we see that this now actually is a sinc type critical point, because the neighboring path lines actually go toward this path line that we're looking at in the middle. So their idea was really seminal, looking at path lines instead of streamlines, but the way that their method works is not Lagrangian and not Galilean invariant and not objective. Similarly, we did that for all the methods that track steady topology, which is like the first intuitive step when you treat time-dependent data. The challenges there lie in the correct association of features from one time step to the next, and to detect the changes in the topology. That means the birth, death, split, and merge of critical points. There are two big groups. One uses linear interpolation in each cell to detect those events, and the other one uses feature flow fields. And all those methods in this category coincide with the steady case. Naturally, they segment the domain, but they are neither Lagrangian nor Galilean invariant, and therefore also not objective. The next group of approaches are the reference frame adaptation techniques. Those are usually not specifically made to generalize flow topology, but the problems that the flow topology encounters is actually typical for other areas of flow visualization too, and so they can be applied there as well. So what we did for the evaluation was pretty much apply the technique and apply the topology on top of that and see if the result satisfies the properties. We found two big groups in here too. One uses the Helmholtz-Hodge decomposition and the other one uses flow stratification. And we can see that these methods have become more successful in satisfying the properties over time, but what they all have in common is that they lack Lagrangianness. Using pathline classification or clustering is based on the idea that streamlines and pathlines coincide on steady fields, and streamlines are the basis for the classical vector field topology, but pathlines describe particle movement in the time-dependent setting. We found that these methods also have become more elaborate over time, but what most of them lack is the coincidence with the steady case. The techniques that belong to generalization of critical points make use of derived scalar fields of the flow that are Galilean invariant to use the extrema or the zeros of those fields to define generalized critical points, like acceleration, the Jacobian, or robustness fields are used for that. And we found that those techniques are usually not objective and not Lagrangian invariant either. A very, very important insight that we gained during our work on this survey is that we are not the only people who have these questions. And scientists in the fields of fluid dynamics and dynamical systems are very advanced and have great ideas that we really have to look into on our side. Clearly, in effect, there is no method so far that satisfies all the desirable properties. There is a lot to do with respect to reproducibility, effectiveness, applicability, uncertainty, scalability, and also topological simplification. And that pretty much brings me to the end of my presentation and to the conclusion of our work. So, in our survey, we tried to go beyond a simple classification and taxonomy of existing techniques. But we wanted to develop a mathematical framework that helps to explain, describe, compare, and discuss existing techniques. And hopefully also in the future helps to close the gaps and develop new techniques that are better. And looking at all the existing work, we came to the conclusion that there is a visible improvement over time. Methods are getting more and more advanced, but still, as of now, there is no method that satisfies all 5 desirable properties. We also learned that other fields and other applications have similar problems, and there's a lot that we can learn from them. And yeah, that concludes my talk. Thank you very much for your attention, and are there any questions?
Thank you, Oksana. I think the first question everybody had is, how would you look like in reality after this presentation? And here you can see. I didn't see any questions coming up. I saw that quite a number of comments came in, but more related to your changing look, Oksana, than scientific questions. So let me start with asking a few questions to you. Oksana, you talked a little bit about the relation to other fields, and you said that we have to carefully look into the other fields and say what they are doing, because they have very similar problems, and we can learn a lot from them. I completely agree with this, but I want to ask the reverse question to you. What can we do that these other communities consider our work and want to look into our work?
Oh, wow. That is a tricky one. I think, first of all, you have to use really, really funny presentations.
Yes, I agree.
No, I'm kidding. So I think what we really have to do is provide the software that we produce in an open source way that is easy to use for other people. And by that, I mean, we might even have to think of being more general than using VTK. So, like, for example, if we could have stuff that just runs on an arbitrary Python array, right? That I think would be much easier for other people to use, because they just are not familiar with VTK, like the people that I'm working with, right? Like, the first thing that we have to do is sit down and figure out how we convert their data so that we can use it, right? The formatting thing is actually, but not the first big question. The other thing is that really there is not a lot of stuff available in a coherent place. Like, as of now, I am actually really working on trying to get the classical flow topology into VTK. And it blew my mind that it was not there. I could not believe it. Like, when I started out as a student hearing about scientific visualization, that already was the oldest technique on the planet, right? And I thought, of course, it must be in VTK, right? But it's not. And now that we have been going back and forth on this merge request for half a year, I can see why, because they are really, really picky with respect to classical. But anyway, right? So we have to make our stuff available, right? This is the first step. The next step is it has to work. by which I mean it has to be robust and really be able to deal with data that looks different than the common street. Because like many of the application scientists that I work with here at Los Alamos, right, they do nukes and stuff, but they do not care too much about smooth fields. Like they have big questions with shock waves and things. And it's really hard for the methods that we like that produce pretty images, right, to run on these kinds of things. And the next thing, it also has to work in a mathematically rigorous way, right? Like what this survey is about, pretty much, right? We give them a picture and we give them a result, but is what we see there really trustworthy, right? That is a question that the application scientists have and that we have to deliver. And as this survey showed, we are not there yet. We cannot really give them a method where they can say, oh, it suffices this, it suffices this. We can trust that the output of this is physically meaningful. So those are, I think, the things that we have to do in order to make other people use our stuff.
Okay. I have another question, actually a question about a part that was not in the talk. In the paper, you did not only bring the classification you presented now, but you also came up with a number of example test data sets, I think 15 or 16 test data sets, that are really nice and simple to make the distinction and explain everything and make sure what is working and what's not. How did you come to this 15 or 16 data sets? What was there a strategy behind, or did you collect them one after the other until you had everything together that fulfills everything?
I might have to give that question back. You mean the little counter examples?
No, not the counter examples, but I think your star comes with a number of test data set, actually, either examples or counter examples. I think there were 13 or 15 test data sets. How did you find them, or how did you come up with them?
I am not 100% sure if you mean like the little counter example, mostly analytical fields as
yes,
data
yes,
sets.
I talk about these analytic ones.
Okay, yeah. So, well, it's pretty much we looked at all the different papers, and from an intuitive and discussion kind of point of view, we started out thinking, do we think this provides this property or it does not, right? And then just try to come up with the most simple example that shows that something does not provide that one. So as an example, your paper, I really have to point out that this is like kind of really a funny coincidence that you are the session chair of this paper, which I, of course, had no idea when I selected one of the papers to put the thing. I really chose it because it's a nice counterexample. And yeah, because it's like so old, because it was really such an early work when you thought about this stuff before everybody else pretty much jumped on that train, right? So in that, for example, I thought, I don't think this method is objective, right? So I went through a bunch of examples until I found one that actually like showed it. So at first I looked at fields that are steady and are just transformed by a Galilean transformation, and I could not find a counterexample, right? So it's not there, but in those cases your method actually works, right? And I had to like make it more complicated until I finally found an example that worked. And so this is like pretty much the approach that I took in those. I used some kind of intuition to figure out which cases might cause the problem, right? Yeah. And Maple for the win. To go through a lot of test cases and say, oh no, maybe it has to change here, maybe it has to change here, and until we've found them. So I think your question aimed at like, could those be test cases in the future, right? To like automatically
is this
test
a complete set of test cases,
right?
for new methods?
It is not at all, because they are completely tailored and like really with the goal, like what is the most simple example so that the reader can just quickly grasp the idea of why this method is not objective or of why this method is not Lagrangian, right? And it will not generalize to upcoming techniques necessarily, right? If they come from the same approach, right, probably in some cases they will, but I think we will have to again handcraft those examples for future techniques.
Yes. Okay. We got not a question, but a comment actually to the question before. Michael Böttinger wrote. We talked about what to do to the other communities. Offer something that solves a problem that can't be solved without visualization. Of course, you are completely right, Michael, with this statement, but it's not that easy. Anyway, further questions. I have another question. On some of your slides, there was this word unclassified appearing. What does it refer to?
Okay, so I mean, I work in Los Alamos at the National Laboratory, which is, a former secret weapon of mass destruction lab and stuff. So it's a very, still today, they do a lot of restricted work, classified work, and things like this, right? So it is required, like in the slide template, that if your work does not contain any classified information, that you put it on the slide. It's yeah, so it's there. It's on every slide except if I put a picture on top of it.
Okay, you want to tell us that you did not really tell us the real secrets about flow visualization. Anyway. All right, these were all my questions. I don't see any further questions in the chat. That means we are at the end of our session. Thanks a lot to Sudhanshu and to Roxana, and thanks to all of you. We had more or less 40 people watching this, which I think is pretty nice and successful. So thanks for all the speakers. Clap to the speakers I see in the chat, and enjoy the rest of the conference. And with this, we are closing the session. Thanks a lot, and bye-bye.